on axial resolution. What's my mnemonic phrase, guys? LARD. What does it stand for?
Longitudinal.
Longitudinal. I heard longitudinal.
Axial. Range.
Radial. Depth. There we go, Lauren. Depth resolution, guys. Longitudinal. Axial. Range. Radial. Depth. Resolution. All describe our axial resolution. Okay? Which is going to be the minimum distance that two structures can be seen apart when they are parallel to the sound beam's main axis. Okay. Remember those key words about it? Again, you're gonna do great on the test. All right. So, axial resolution is not adjustable. The spatial pulse length is fixed in the transducer. Axial resolution is directly related to the spatial pulse length. It's determined by it. Okay? We can't change the spatial pulse length, right? What can we change?
Depth.
Depth, which is what? Changing our listening time, right? That's what we can change, our listening time. Okay? Remember, our pulse length is fixed, just like our wavelength. It's fixed in the transducer. We can't change those. Okay? So no, it is not adjustable. All right? Our typical values are going to be from 0.1 to 1 millimeters. Okay? Lower numbers indicate shorter pulses and improved image accuracy. Okay? The lower the number, the better the axial resolution. That's all that's saying. Okay? So a typical value of 0.1 millimeters is going to have better axial resolution than 1 millimeter. Okay? Myra, here we go. Okay. Again, guys, lower numerical values of axial resolution indicate shorter pulses. Okay. So if I have a spatial pulse length, one is 10, one is 5. Remember how did I tell you how to determine a spatial pulse length? Without even going over it yet. We haven't even got to it yet, but I know I told you like 3 or 4 times. Medium. What's the formula for determining spatial axial resolution?
Spatial pulse length divided by 2.
Spatial pulse length divided by 2, guys. So if I have a transducer that's a 5 megahertz transducer and a 10 megahertz transducer, which one is going to have? Well, that's not a good question. Because I'm not telling you the pulse. So if I have a spatial pulse length that's 10 millimeters and 5 millimeters, which one is going to have the best axial resolution?
10.
5. The shorter the better.
The 5 millimeter transducer is going to have the better axial resolution. So we like lower numerical values. Therefore, our axial resolution is going to be in 5 millimeters for the 10 millimeter transducer and 2.5 for the other one. So we want the lower numerical value, which is going to be the 2.5. All right. Shorter pulses create more accurate images. We know this already. Therefore, image quality is better when axial resolution has a lower numerical value. Okay. The mathematical description of axial resolution is right here, guys. Okay. Again, I already told you what it is. Axial resolution is equivalent to spatial pulse length divided by 2. Okay. Also, axial resolution is equal to the wavelength times the number of cycles divided by 2. Wavelength times the number of cycles is the spatial pulse length, right? Right? We learned that in chapter 3. Chapter 3. All right? In soft tissue, axial resolution is directly related to the number of cycles in a pulse and inversely related to the frequency. Remember we talked about this last time? If it's on top of the equation, that's a direct relationship. If it's on the bottom of the equation, it's an inverse relationship. Sophie likes those.
You can see inverse to it.
I like it. I like it. Okay? Probably not going to have you guys doing math problems unless, you know, because there's not going to be questions like that. I may have you give the spatial pulse length and ask you to tell me what's the axial resolution based on that. I may give you the number of cycles and the wavelength and have you figure it out that way. Okay? Not going to have us going through 0.77 times the number of cycles divided by the frequency. All right? So what allows some transducers to have better axial resolution than others, guys? Axial resolution being determined by the pulse length yields shorter pulses with improved axial resolution. A short pulse is going to be created in 2 ways, guys. 2 ways. We talked about this already. A pulse that has less ringing, you know, a thicker dampening element, okay? And a pulse that has higher frequency, okay? So those are going to be shorter wavelengths, right? So it's going to be able to get in between those structures that have the minimum distance between them. All right. So when we're talking about less ringing occurs when a pulse is short and there are a few cycles in the pulse. Okay. Remember, more than one cycle makes our pulses, right? So the cycle is just a compression and a rarefaction, right? One up, one down. That's the cycle. Okay. Just like this one right here. How many cycles is this?
2.
2 cycles compared to 1, right? The one on the bottom is going to give us better axial resolution, right? Because it's a shorter pulse. Okay? Even though we know in ultrasound we use 2 to 4 cycles to make a pulse in diagnostic ultrasound. This is just for illustration purposes. All right? Transducer designs have developed ways to create pulses that are only 2 or 3 cycles in length. Okay? That has a lot to do with our damping element. Okay? One way to reduce ringing is to use a damping element. Okay? But that's how we're going to affect our axial resolution. Number 1 would be less ringing. Number 2 would be higher frequency. Right? So there's higher frequency right here, guys. Both in this image right here, both of these pulses consist of 4 cycles. Everybody can see the 4 cycles? Everybody? 4 cycles? Okay. But we can see the wavelengths of the top cycle is a lot, the top pulse is a lot longer. These wavelengths are longer, right? The wavelength is the distance from the beginning of the pulse, beginning of one cycle to the beginning of the next cycle, right? So this distance from here to here is a lot longer than the distance from here to here, okay? So that would let us know that shorter wavelengths equals higher frequency, inverse relationship, okay? A pulse is short if each cycle in the pulse has a short wavelength. Short wavelengths are characteristic of a higher frequency sound. Pulses made up of higher frequency cycles have superior or better axial resolution. We love those for our ultrasonic images. All right? I'm taking my time. I feel like I'm still blazing. I feel like I'm still going through this really fast. All right, guys? So, better axial resolution is associated with all of the following, guys. Shorter spatial pulse length, right? We love short spatial pulse length because that's going to give us the best axial resolution. All right? Short pulse duration. That's also related to axial resolution, correct? But I want you guys to know that it's determined by, that question never comes up. What is axial resolution determined by? The spatial pulse length. But it's related to pulse duration. Okay. Better axial resolution is associated with higher frequencies because they provide us with shorter wavelengths. Okay. And fewer cycles in a pulse, which equivalent to less ringing. Okay. That's going to be done by our damping element. The damping element stops the resonant frequency, stops our pulse, our sound from vibrating, our PCT from vibrating. Okay. And axial resolution is better with lower numerical values. Okay. What's our typical values for axial resolution? 0.1 to 1 millimeters, guys. 0.1 millimeters to 1 millimeter. Okay? Guys, another image right here of axial resolution. The ability to separate structures that are parallel to the sound beam's main axis. Okay? Front to back. Front to back. Similar, just like this. So here's the example it has in the book, guys. This one has no numerical values, so we really don't know. But we can clearly see that the bottom transducer is yielding a higher frequency than the top one, right? Therefore, these two right here, these aren't very close, right? These aren't very close, so both of these are going to provide us with, and the ultrasound is going to be able to see both of those as separate structures, okay? When we get to this group right here, this higher frequency transducer is still, even though they're this close, it's still going to be able to separate both of those structures from one another, okay? Or if we look up here, man, I'm sorry I took this picture with my phone. Where we look up here, these two structures, they're very close, but that's a lower frequency transducer, and it's just showing these structures as one image. Okay, these are the true reflectors at the top. Okay, this is lower frequency, high frequency, and this is how they appear on the image. Okay, so these two reflectors are very close together. Lower frequency transducer can't separate them. We're going to represent them as one structure. Okay. Any questions, guys, about axial resolution? Y'all already knew this, most of that stuff already, right? Sure.
Thank you.
You need that?
I just need to know.
You good? Yeah. Oh, there it is. Low numerical values. All right. So, of course, we got review questions, guys. Review questions. Okay? Guys, the ability to distinguish two structures lying close together, front to back, or parallel to the sound beam is called. Hold up, before we even do that. What's the definition of resolution?
The ability to create an accurate image.
No.
The ability to create an accurate image.
Ah, there we go. What is it, Uber?
The ability to create an accurate image.
Absolutely, that's what resolution is. Do not be confused. Do not be confused. Okay?
What was that, Uber?
The ability to create an accurate image.
Bang, bang. I love it. I love it. I love it. Okay? So, on to number one. The ability to distinguish two structures lying close together, front to back, or parallel to the sound beam is called
Axial resolution.
axial resolution. I'm waiting. I have 4 more, right? Myra.
Are we voting?
Huh?
Are we voting?
No, we're not voting. I'm waiting on my synonymous terms. That's what I'm waiting on. 1.
Axial resolution.
Axial resolution. What else? Longitudinal.
Oh.
Axial.
Range.
We already said axial. We already said axial.
Radial.
Range.
Resolution.
Yeah.
Okay.
Okay. Those are our synonymous terms for
Depth.
axial resolution. I don't know what y'all are doing. Y'all don't put y'all hands up when I ask y'all to vote in the class, and I got everybody's hands up like this. What's going on in here?
You said I'm waiting on one.
What's going on in here? Y'all something else. So again, longitudinal, axial, range, radial, and depth. What's our mnemonic phrase for that?
Lord.
Lord. Lord.
Not Lord.
Lord.
Not Lord. That's Ebonics for Lord right there. That's when you go in a black church, they say Lord. No, we ain't talking about that right now. We talking about Lord. We talking about Lord. Not the loud.
Not the loud.
All right. Again, next one, guys. Number 2. High or low frequency transducers have the best axial resolution. Mr. Seal. Higher frequency transducers have the best axial resolution.
Yes or no?
Yes or no?
High or low frequency transducers have the best axial resolution.
Higher.
Higher frequency transducer, guys, have the best axial resolution, guys. We just talked about that on the previous slide right here. Higher frequency transducer is better able to distinguish two structures that align parallel to the sound beam's main axis if they're close together. Okay? So definitely, Mrs. Seal, good job. High frequency transducers. Number 3, guys, in soft tissue, a 3-cycle 1 megahertz pulse has a pulse length equal to 8.5 millimeters. What is the axial resolution, Adelie?
She has to use the equation, right? And the formula.
What is the axial resolution, Ms. Sanchez? We patient. We got number time.
8.5.
That's all we got.
77.77.
Guys, please don't pull out your calculators for this. Somebody help her out. Somebody help her out.
4.25.
4.25, guys, our axial resolution, right? Because our axial resolution is equal to the spatial pulse length divided by 2. Our pulse length is equal to 8.5 millimeters. Half of that is 4.25. Don't get, I told you guys, don't let all the fluff get you. Don't let all the fluff get you. You already know how to determine axial resolution. Okay? It's telling you the spatial pulse length right there. It don't matter if it's 3 cycle, 1 megahertz, unless I'm comparing it to something else, right? Right? So I'm asking you, what is axial resolution? 4.25 millimeters, guys. 4.25 millimeters. Okay? Number 4, Sofian. If a new pulse transducer has much less cycles in its pulse, the image accuracy improves, degrades, remains the same. What happens to image accuracy?
Improve.
Improve. Man, that's my guy right there.
Yes.
The image accuracy improves because it now has much less cycles. Remember, we
Higher
like
frequency.
much less cycles, right? Less ringing. Less ringing. It's going to give us better axial resolution.
But more pulses. More pulses though.
Why are there more pulses?
No, less cycle.
Less cycles. Remember,
Less
cycles
pulse.
make up pulses.
Right, but you want more pulses.
Is it going to make them shorter? I don't want more
It's
pulses.
short
That has
pulse.
to do with PRF and PRP. We're not on that. We're not on that. Remember, our 2 ways to have the best axial resolution would be less ringing, higher frequency. Okay? We have less cycles in the pulse. Our image is going to be improved with axial resolution, or radial resolution, range resolution, depth resolution, longitudinal resolution. Okay? Know our synonyms, guys. Know our synonyms. Okay? Any questions on these 4 questions? Any question on these 4 questions?
We want more questions.
One more question. I wanted to add more. But, you know, this chapter's kind of short. I can't give you all my test material. Goodness, dude. You think you slick, brother. You think you slick. All right? Real quick, guys, before we move on. Axial resolution. Any questions? When it comes to the numerical values, what's going to give us worse axial resolution?
The higher.
Higher frequency.
Okay, y'all paying attention. Everybody clear on that?
Yep.
Everybody good on that?
What?
Alright.
The
Go ahead.
higher
Go
the
ahead.
numerical value by
Huh?
resolution. What numerical value?
Remember, what are typical values for axial resolution?
0.1 to 1 millimeter.
So, better axial resolution is associated with lower numerical values. Okay?
Where we would see these numbers?
You'll see these numbers if I gave you 2 spatial pulse lengths, and I'm asking you which one is going to provide us with better or worse axial resolution. Okay? The lower numerical value is going to have better axial resolution than the higher numerical value. Right now, I just kind of flipped that question, and my people were listening. Good job. All right, guys. No questions on axial resolution? Goodness, y'all are impressive. Time for lateral resolution, guys. Lateral resolution. Y'all already know what this is as well. Okay? Lateral resolution measures the ability to distinctly identify 2 structures that are very close together when they are side by side or perpendicular to the sound beam's main axis. Okay? Here's our sound beam traveling this direction, right? Sound beam traveling to me. Okay? These 2 structures right here, they're side by side or perpendicular to the sound beam's main axis. Okay? They're gonna, when they collide, it creates a 90-degree angle. These are no longer front to back like axial resolution. Okay? They're side by side. All right? We're clear? Y'all should be looking for those key words, right? When I'm asking about resolution. Like the bolded words I have on this board. Side by side and perpendicular. Okay? Lateral resolution. Okay? It answers the question, what is the minimum distance that 2 structures positioned side by side or perpendicular can be apart and still produce 2 distinct echoes on an ultrasound image? Okay. How close can 2 structures be side by side and still represent their own part of anatomy? Okay. And that's our image right there. We're going to remember I kind of drew that last week. We're going to talk about that a little bit later.